visible? If not, kindly, I had shared my presentation. If it is not visible, kindly type in chat box. Okay. Thank you, Ranjan, for your feedback. Now I'll start the propagation effects on a satellite system. So what are this propagation? So let us see propagation and its effects on the satellite systems. Okay, the Earth station, the space satellite, which is used for communication, all comes under satellite systems. So the significant effects observed in the frequency bands below 3 gigahertz occur primarily in the ionospheric region. What happens in this ionospheric region? Let us see that. So the ionospheric region consists of ionized gases or plasma that extends from about 50 kilometer to having an upper limit of about 500 to 2000 kilometer from the Earth surface. So from 500 kilometer to 2000 kilometer approximately from the Earth surface, all the space has so much of ionized gases or plasma materials. So this tends to observe, diffract, refract, or transmit the satellite signals. So the effects due to that is a type of propagation effect. So the ionosphere is ionized by solar radiation in either ultraviolet or X-ray frequency range, which will have free electrons and positive ions so as to electrically neutral it. Hence, only a fraction of the molecules such as oxygen and hydrogen will be ionized, and a large number of neutral molecules will also be present. So this is the free electrons, the large number of neutral molecules are the free electrons that affect the electromagnetic wave propagation for a satellite communication. These free electrons. So the complex nature of ionospheric physics and the interaction of communication system affects the ionospheric effects. That is always a task for us to solve by using any of the analytical models or the prediction models. So in many cases, the only recourse available to the systems engineer is to review the limited data if it is available, or to attempt to summarize the effects of this into ranges or bounds for the expected degradations. So let us see what are these effects. So the first is your general link propagation parameters. So let us see what it is. So the link parameters that are degraded by the background ionization are Faraday rotation, group delay, time delay, dispersion. This topic presents several procedures for determining several important propagation parameters for satellite systems operating below 3 gigahertz. Below 3 gigahertz. So these systems are generally applicable to fixed slant path conditions, that is FSS, fixed satellite service, BSS, broadcast satellite service, space research SR, space operations SO, and other applications that apply only fixed ground terminals, where the satellites will be a fixed, which are used for fixed services. In addition to the Faraday rotation, group delay, and timed dispersion, the ionospheric scintillation, aurora absorption, and polar cap absorption are also present, which plays a major role in degrading the satellite communication link. So here I elaborate you an procedure for identifying or for summarizing as how to identify whether the signal that is propagating is affected due to these parameters. Okay, so the system parameters required for this propagation analysis are frequency of operation measured in gigahertz, the period of time which is used to achieve the desired performance on an annual basis, the polarization tilt angle measured in degrees, the elevation angle to the satellite measured in degrees, the latitude of the ground station measured in degrees, longitude of the ground station measured in degrees, and the altitude of the ground station above sea level. So all this 7 system parameters are required for analyzing an propagation effect. Frequency of operation, period of percentage of time, polarization tilt angle, elevation angle of the satellite, latitude, longitude, and altitude of the ground stations. And most of these parameters for ionospheric propagation require a TEC value. TEC represents total electron content, which lays as the first step in the process of analyzing the propagation parameters. So this TEC value is usually quoted for a zenith path having a cross section of 1 meter square. This total electron content of this vertical column can vary between 10 power 16 to 10 power 18 electrons per meter square. So for many purposes, it is sufficient to estimate electron content by multiplication of the peak electron density with an equivalent slab thickness value of 300 kilometers. So next we'll see an important consideration for satellite link design. Always when we design a satellite link, the uplink design is easier than the downlink in many cases. Why? Because at Earth station we can give high boosting powers. If necessary, or the Earth station will use high power transmitters. So the Earth station transmitter power is set by the power level required at the input of the transporter, either using a specific flux density that is required at the satellite, or a specific power level that is required at the input to the transporter. Then the analysis of the uplink requires calculation of the power level at the input to the transporter, so that uplink carrier to noise ratio can be found easily. So this carrier to noise ratio determination is an important concept such that requires the power level to be determined at input as well as output of the transponder. So this transponder will be present in the satellite, which is used to receive the uplink frequency signals and then repeat it, amplify it, and send it to the receiving Earth station. Then with a smaller diameter Earth stations, a high power Earth station transmitter is required to achieve a similar satellite of having the same equivalent isolated radiated power, EIRP. Then the uplink power control can be used against an uplink rain attenuation. So let us see what is this rain attenuation is. Okay. So the propagation effects and their impacts on the satellite is to be considered why? Because this lays as a basic fundamental of the communication link. In a satellite communication link, the breakage of link occurs mainly due to the loss on the Earth's atmosphere signal. So which could be due to atmospheric absorption, which is arise due to gaseous effects, the cloud attenuation, which could be due to aerosolic and ice particles, which could be due to tropospheric scintillation, which are due to refractive effects, then due to Faraday rotation and ionospheric effect. Another ionospheric scintillation is second ionospheric effect, and then due to rain attenuation and due to rain and ice crystal depolarization. So out of this, we had seen about the attenuation concepts. Already you would have studied in microwave frequencies, microwave engineering, the Faraday rotation in electromagnetics. So we'll be concentrating on the rain attenuation, which is an unfamiliar topic for you all. So the rain attenuation is the most important feature to be addressed for frequencies above 10 gigahertz. About 10 gigahertz, when we use the frequency, obviously we will be suffering with rain attenuation when only rain falls. If there is no rain, we need not bother about it. But rain will definitely fall either today or tomorrow, is unpredictable. So for that, if rains are being predicted, accordingly the design in amplification or design in the system should be appropriately measured. So for that, we'll be using rain attenuation models, which are derived by Crane in 1982 and 1995, CCIR 1983, ITUR in pages 618 to 5. Rain attenuation models are being developed further. So you can see the geometry of satellite passing through the rain. We have a sea level, you can see at the bottom a sea. From that level, we are having an Earth station. The Earth station is focused towards the satellite in space at an elevation angle. So the distance between the Earth station and the satellite is taken as L, and suddenly rain comes. So when rain comes, the link will get scattered, or the link will get disturbed, or the amplitude in measurement of voltage will get minimized. So attenuation plays a major role. So this is your structure for that. And then on analysis, it was done by Kirkkonummi, Finland, during the year 1979 to 1989. Okay. So the total atmospheric attenuation during this 10 years at this place, Kirkkonummi, can be calculated like this. Consider in 79, it was about 8.2 or 8.3. The total atmospheric attenuation measured in decibels was in certain that much. In 1980, the atmospheric attenuation was lower, it was around 7. In 1981, it was around 11. This is obtained for a frequency of 12 gigahertz. 12 gigahertz frequency with an elevation angle of 20.5 degrees, vertical polarization. Okay. And during 1983, it was the highest peak. So it was around 12. 12 decibels was attenuated. So then in 1984, it was around 9. And around 1985, it was nearly 11. 1986 is this curve, which is in dashed lines. So this dashed lines is nearer to 10. So it is about nearly 9.8 or 9.7.
இப்போ ஃபர்ஸ்ட் மேட்ச் எல்லாத்தையும் எடுத்தா போட்டானுங்க அப்புறம் இன்னும் கொண்டுது இதெல்லாம் 3 மேட்ச் நான் ஃபர்ஸ்ட் ஜெயிச்சேன் அப்புறம் அவனுங்க 3 மேட்ச் ஃபர்ஸ்ட் ஆனாங்க
So in the year 1986, the attenuation was around 9.8 or 9.7, which is the dashed lines. representation. So that was in mid year. Then in 1987, it came around 8.2 over the frequencies. Yeah, it is over the frequencies. Then in 1985, it was around 11. 1988, we should say 1988. It was around 10. 1989, it was around 11. So this graph of attenuation measurement over the region of Kirkkonummi in Finland was taken for years 1979 to 1989, which predicted that, or which gave us an information that where we had a higher attenuation means that year experienced more rainfall cumulatively. And where we had lower atmospheric attenuation, it could be the case that it had a more dry season rather than rainy season. So this is how the data has been predicted or data is being taken out. So the effects of the propagation on direct broadcast satellite systems. So the majority of the currently available broadcast satellite services where we use it at DTH, direct to home, operates in KU band. KU band. The allocated bands are in the range 11.7 to 12.5 gigahertz in region 1 and 12.2 to 12.7 gigahertz in region 2 and 11.7 to 12.2 gigahertz for region 3. The uplink or the feeder links generally operate in 17.3 to 18.1 gigahertz band for this above KU band downlink. So this is the frequency bands of KU, of downlink and uplink that is used in DTH, direct to home systems. So these direct to home systems generally operate with a small aperture antenna that are designed for unattended fixed point operations, where the broadcast satellite service for the downlink tends to be higher in power by 6 decibels to 10 decibels. So the BSS system performance is often specified with reference to worst month link availability rather than an annual basis. The analysis also can be done in such a manner. Rather than doing cumulative analysis for every month, you can see where the attenuation or the propagation effect is more in which month. Accordingly, we can design that satellite. The main propagation effects that must be included in the evaluation of KU band broadcast satellite service are atmospheric gases attenuation, rain attenuation, cloud attenuation, wet surface effects. Atmospheric gases attenuation, rain attenuation, cloud attenuation, wet surface effects are the propagation effects that should be considered while designing a satellite to operate in Ku band for the service of broadcast satellite service. Let us see the rain attenuation. So this rain attenuation comes into play only when the operating frequency is about 10 gigahertz. So the consideration described here would apply to only of this following bands. One is Ku band, another one Ka band, another one Q bar V band. The propagation considerations for non-geostationary orbit links, which is NGSO, operating bands below 3 gigahertz is not considered here. Why? Because the rain attenuation is a factor for only, it occurs only for an frequency, operating frequency of the satellite, which is about 10 gigahertz. So below 3 gigahertz, our rain will not come into picture. Rain attenuation is not considered because though rain comes in that band, if rain comes and if you are using 3 gigahertz band, the propagation is not affected. Okay. So the evaluation of propagation effects involving this non-geostationary orbiting satellites is complicated by the fact that slant path to the satellite is no longer fixed. Is no longer fixed, but there will be a time variable parameter which is used. So the statistical prediction models for the rain attenuation, rain and ice depolarization, tropospheric scintillation are all based on a fixed elevation angle to the satellite. Let us see for an example. As an example for LEO satellites, low Earth orbiting. A satellite having a typical orbital period of 1.5 to 2 hours will pass over an area of the Earth's surface several times per day. The elevation angle statistics must therefore be integrated into the propagation prediction procedure to assure the proper evaluation of propagation margins to be achieved. So consider a low Earth orbiting satellite, LEO satellite, In a circular polar orbit at an altitude of 765 kilometer with an ascending node at 1000 watts. So if it is 1000 watts, then it should be an larger LEO satellite. And assume that the feeder link operating is in Ka band. And with a feeder link link terminal, Yeah, there was a breaking link. Sorry for that. So let us see the topic, depolarization. So rain depolarization is also calculated via the same techniques as we had seen applying it for rain attenuation. Okay. So then if the technique is same, why two different names? Is that the difference lies in examining the depolarization. We assume the raindrops to be oblate spheroids. The raindrop is generally at a random orientation with respect to the electromagnetic wave direction. So which is specified by an angle Q. The orientation is specified specifically denoted by Q angle between vector of propagation and the axis of symmetry of raindrops. So the component which is vertical is parallel to the minor axis of the raindrop and hence less water content. And it's the case of quite opposite for the horizontal. So as a result, there will be a difference between the attenuation and a phase shift of electric field component. So which leads to depolarization. So this is known as a differential attenuation and differential phase shift. So this differential attenuation, differential phase shift leads to depolarization of the signal. Forgot to put L. So for a geostationary Earth orbiting satellite that transmits a linear polarized wave, the horizontal polarization is the case where electric field is parallel to Earth's equatorial plane. And vertical polarization is where the Earth's electric field is parallel to Earth's polar axis. So this is how we determine horizontal polarization and vertical polarization. And a geostationary orbit satellite transmitting linearly polarized wave is called to be as horizontal polarization when electric field is parallel to Earth's equatorial plane. Parallel. And if the same Earth's electric field is parallel to Earth's polar axis, then it is vertical polarization. So the main idea of polarization is to bring down the interference between the different signals that belongs to different frequencies and introduce frequency reuse when the signal passes through atmosphere. Sometimes an additional orthogonal signal might be generated that leads to the effect of depolarization and interference. The cross polarization discrimination ratio of received coplanar, copolar, and the generated cross polar is measured in decibels due to rate. The next topic is the atmospheric losses. So this is the last topic of the presentation, as well as unit number 2. So till now, if you have any queries, you can type in chat box. I'll give you another 5 minutes. Okay, 5 to. I'll give you another 5 minutes. If you have any queries, till this you can type in chat box. Then I'll proceed with the atmospheric losses. Some 4 or 5 minutes time, then we'll proceed further. Since there are no queries in the chat box, I proceed further on to the last topic called as atmospheric losses. So atmospheric loss is a kind of loss which is derived from the absorption of electromagnetic energy by atmospheric gases. So they are of two different types. One is atmospheric attenuation, another one is atmospheric absorption. So the major distinguishing between them is the major difference between the attenuation and absorption is that attenuation is weather related. When rainfall, snowfall, or thunderstorm or sandstorm occurs, attenuation will come into play. While absorption comes under clear sky conditions. Some part of the particles or ions present in space will absorb even during clear sky conditions. So let us see the ionospheric effects. So all the radio waves transmitted by satellite to the Earth or vice versa will obviously pass through the ionosphere, which is the highest layer of atmosphere, which is lying between 500 kilometers to 2000 kilometers, having fully ionized particles, which is a result of the action of sun's radiation. So free electrons are distributed in these layers and clouds of electrons would be formed, which is known as traveling ionospheric disturbances. So the effects due to this traveling ionospheric disturbances are polarization rotation, scintillation effects, absorption, variation in the direction of arrival, propagation delay, dispersion, frequency change. So these effects decrease usually the increase of the square of the frequency, and most serious ones in satellite communication are the polarization rotation. After the rain, we are going to see about cloud and fog, which this cloud and fog can be categorized as hydrosols, which are suspended droplets of liquid water. Suspended droplets of liquid water that are less than  Next topic is about clouds and fog. So these clouds and fog can be categorized under hydrosols. So these hydrosols are suspended droplets of liquid water, which would be having a diameter of less than 0.01 centimeter. So this hydrosols becomes significantly notable for systems operating about 20 gigahertz. So about 20 gigahertz, when we use the frequency for satellite communication, then clouds and fogs come into picture. The attenuation increases with increasing frequency and decreasing elevation angle. So portions of clouds and fogs that are frozen do not cause significant attenuation, though they may be responsible for signal depolarization. So further, attenuation may not be responsible, but depolarization will occur. So for a high margin systems, rain attenuation is dominant impairment. For low margin systems and high frequencies, clouds represent an important impairment. So rain occurring less than 5 to 8% of the time, whereas clouds that are present 50% of the time on average can have a constant coverage of continuous intervals up to several weeks. So the modeling cloud attenuation requires knowledge of cloud characteristics along the slant path. The liquid water droplets remain the main source of attenuation. Ice particles are also present as plates. Ice particles are also present as plates and needles in cirrus clouds, or as larger particles above the melting layer in rain clouds. However, ice is not a significant source of attenuation and is usually neglected. The main interest is in non-precipitating clouds with the spherical water droplets less than 100 micrometer diameter. So the upper bound would be a requirement for the droplet to be suspended in clouds without strong internal updrafts. So as a result, the Rayleigh approximation comes into picture, where the particle size would be of 100 micrometers for frequencies about 300 gigahertz. So here we call this property of the cloud to be as CLW, cloud liquid water. The accurate measurement of the cloud liquid water plays an important requirement in determining cloud attenuation. The accurate measurement of this CLW would be an important requirement in determining cloud attenuation. So where the cloud temperature is also needed to be considered. Which is computed from the dielectric constant of water. So far that two models have been proposed for dealing with the clouds and fogs attenuation on a satellite path, which is the cloud attenuation model and the sloping cloud model. Let us see them. The cloud attenuation model provides and information to calculate the attenuation along the Earth space path for both clouds and fog in according to the recommendation of International Telecommunication Union. This was adopted into a recommendation in 1992 and has been updated in 1994 till 1999. So this is valid for liquid water only and is applicable for systems operating at up to 200 gigahertz. So the necessary parameters are frequency, operating in a gigahertz, elevation angle measured in degrees, surface temperature measured in Kelvin, and the total columnar liquid water content measured in kilogram per meter square. So for every meter square, how much amount of total columnar liquid water content is available. So an intermediate parameter required for the calculation is the inverse temperature constant, phi, which is 300 by T, where T is the temperature measured always in Kelvin. For cloud attenuation, assume the temperature is around 273.15 Kelvin. So when you substitute, we get the phi value as 1.098. For fog attenuation, T is equivalent to the ground temperature, and then the procedure is same. Phi is equal to 300 by the ground temperature, substitute, and you will get phi value. So after this, we need to follow this following procedure to determine the cloud attenuation model. So first is to calculate the relaxation frequencies. So the primary and the secondary relaxation frequencies Fp and Fs as used for the double Debye model for the dielectric permittivity of water. Fp will be 20.09, which is a constant value, minus 142, phi minus 1 plus 294, phi minus 1 square gigahertz. That would be your frequency of primary determination. Similarly for secondary, 590 minus 1500, phi minus 1. Then we need to find complex dielectric permittivity. Complex dielectric permittivity. So this complex dielectric permittivity can be obtained from the real and imaginary components of the dielectric permittivity of water. So this is out of our determination. So these are specific examples for that. Next is the rain and ice effects. At frequencies above 10 gigahertz, rain is dominant factor in satellite propagation. The long-term behavior of rain rate is described as a property called as cumulative probability distribution and known as exceedance curve. We'll see that exceedance curve also. So this exceedance curve will give us the percentage time that rain rate exceeds a given value. So there are mathematical models that are available giving the exceedance curve for a given location based on the total rain accumulation and other meteorological data. So rain attenuation and depolarization occur because individual raindrops absorb energy from radio waves, and because some energy in the waves is scattered out of the propagation path, these interactions depend on the number of raindrops encountered and on their distribution of sizes and shapes. If rain rate R is constant over a path, the attenuation A caused by the rain is given by this equation. A is equal to R power B L decibels. The quantity A R power B is called the specific attenuation. The coefficients A and B depend strongly on frequency and weakly on polarization. The raindrop temperature and other factors in practice, the AN value will depend on frequency and polarization, which can be obtained as A value as given in equation 3.1.3 for frequencies between 2.9 to 54 gigahertz. It is 4.21 into 10 power minus 15. And if it is between 54 gigahertz to 180 gigahertz, it is 4.09 into 10 power minus 2. Its polarization of frequency values at the top. F is the frequency in gigahertz. So again, we have sea level, we have the Earth surface, we have the Earth station, the satellite in space, and we have the cloudy structures in between them. L is the path length, slant path length L, which can be calculated by He minus Ho divided by sine EL. EL is the elevation angle with respect to the Earth station. He is the height being measured from the satellite to the Earth surface sea level, and H0 is the distance from the above the sea level, distance to the distance of the Earth station it is present, so that divided by sine of the elevation path EL. So with that we can find out the L value. In addition to the absorption and depolarization that it causes, rain also degrades the performance of satellite communication systems. By increasing the Earth station antenna noise temperature. If there is a clear weather, the antenna sees the cold background of space, but in rain, it receives thermal radiations from raindrops. The increase in antenna noise temperature due to rain can be estimated by TB is equal to 280, 1 minus E power minus A divided by 4.34 Kelvin, where A is the rain attenuation measured in decibels. And this should be added to the clear weather antenna noise temperature when calculating carrier to noise ratio in the rain. The number 280 in the above equation is called the effective temperature of rain. It differs from true temperature because of scattering and antenna effects. In some conditions, there would be an increase in temperature, maybe more dominant than attenuation caused due to rain. If a satellite link is maintained during rainfall, it is necessary that enough extra power called power margin be transmitted to overcome the maximum. during rainfall, what the satellite will do is that it will sense it, and an extra power will be transmitted to overcome this additional attenuation that is induced by the rain. Okay, so for that, sensors will be deployed. So the diagram shows, the graph shows the rain attenuation as a function of rainfall for different frequencies. You can have that 3 gigahertz, 4 gigahertz, 6, 8, 10, sorry, 8, 11, 16.5 gigahertz frequencies. During that, how much amount of attenuation has been taken place with respect to rainfall. Okay, rainfall measured in millimeter per hour. If operating at a frequency of 3 gigahertz, you can see that if the rainfall is 3 millimeter per hour, for every hour there is a rise or there is an fall of 3 millimeter rain on the earth, we get attenuation of about 0.001 decibels per kilometer. For every kilometer, 0.001 decibels per kilometer is added. So if the distance between the satellite is 36,000 kilometer, so 36,000 into 0.001 is your decibels per decibels for 36,000 kilometer at frequency of physical 3 gigahertz would be your attenuation due to rain. Similarly, you can find it for the other frequencies also. For example, if the rainfall is around 20 millimeter per hour, you can see how large it is. For every hour, there is a rise in uh, height of water falling on the earth of about 20 millimeter or 2 centimeter. You can see. You can see. I will show you this. Right. 20 millimeter. There is attenuation in 3 gigahertz itself as approximately, I think so, 0. You can see that from here. It is 0.005. So into the distance it is being traveled. Okay. Into 36,000. So that much is your attenuation. So this is how to calculate. So I have another rainfall attenuation with respect to elevation angle. So average path length in y-axis and elevation angle measured in degrees in x-axis. You can see if there is an elevation of 10 degree, the rainfall is 150 millimeter per hour. You can see average path length will become approximately 3. Then you can see similarly for 100 millimeter per hour, 50 millimeter per hour, 25 millimeter per hour, 12.5 millimeter per hour, 5 millimeter per hour, 2.5 millimeter per hour, 1.25 millimeter per hour. So if these are the dimensions where rain falls on the earth, so the appropriate path length will tend to decrease. If the path length tends to decrease, then obviously what will happen? The communication link will get destroyed or the propagation effects will increase. So these are the two graphs. So any queries you can type in chat box. If you have any queries in today's presentation or in the earlier presentation of Unit 2, you can type in chat box. So since there are no queries, I would like to show you an diagram of the satellite structure. The satellite structure which are being separated into parts. If you see how it is. Okay. You can see right from the left hand side we have a drag panel, which is meant for generating power, solar panels. Then we have the COM components, which consists of a third tray, which is called as third tray, having the COM communication components, COM. Then in the second tray we have battery. Then we have the main power control unit, which is green color here, which is present in the second tray, along with the antenna. So the antenna used is your ultra high frequency bands antenna structure, which is optimum for that. Then we have the first tray. So the first tray will have your AOC components. AOCS is your main components, which is attitude control and orbit control. Okay, attitude components in that. Then we have the S-band antenna and the GPS antenna. Then we have again the drag panel, so which is a solar panel. So we have a covering LV separation mechanism. Then we have inter-satellite separation mechanism. Okay. So this is your satellite structure. And I would like to show you the Hughes system 376 spacecraft. So this is your structure of that. Having a telemetry and command antenna at the top, which you had seen TTC, telemetry tracking and command antenna. Then we have an antenna reflector. We have an antenna feeder in the left hand side. Then a thermal radiator, a control thruster in the center, a propellant tank for which acts as your booster to the rocket. Then we have the apogeic motor. Then this side we have the solar cells array supplying power in space. Then we have the battery pack. We have the traveling wave tube amplifier, TWT amplifier for amplification of your signals. Then we have disp and repeater shelf. This is HS-376 spacecraft. Yeah, this is an example of satellite uplink and satellite downlink all together. At the top you have a satellite which is present in space. So either side can be acting as uplink or downlink, it doesn't matter. So I'm taking left side as uplink chain. So from the router, whatever might be, all the users, mobile equipments, devices, systems are routed through an router, and then it is modulated through a modulating system which acts as your intermediate frequency, IF stage. So from there it is up converted to C band, X band, Ka band or Ku band. You can see here C band, X band, Ka or Ku band depending upon application. Then it is power amplified, and through the waveguide, mostly we'll be using a microwave guide, it is sent through an satellite dish in Earth station. This is completely in Earth station, and this is called as uplink system, and the frequency used here is uplink frequency. So then it is sent to the satellite. The satellite receives the signals, the antenna in the satellite, it repeats, it amplifies, then it sends it to the receiver through the downlink frequency or through the downlink system. Again, the satellite at a farther distance from the transmitter is present and it receives the signals through the satellite dish, then to the waveguide, then we have a power amplifier, then it is down converted, then it is demodulated and sent to router again for all the corresponding users. So this is an example of satellite uplink and downlink. So next, I'll show you this. What is present inside this satellite here? So this is what is present in the satellite. X-band antenna, very specific. X-band, S-band. We have a camera. We have a star tracer, star tracker. We have a payload equipment. We have buses interconnecting them in yellow color. We have GPS antenna for determining latitude, longitude positioning. We have a thruster, and then the solar panels. All.